The first alert hit at 02:13, high severity, pager duty, external API error rate above 35%. I was already half awake when Slack started lighting up. Payments failing in EU region. Seeing spike in 401s from third-party provider. Is this us or upstream? I pulled up Grafana. Latency was normal. CPU was fine. Pods were healthy. But error rate was climbing, fast, from 2% to 18 to 41. And the weird part? Only one service was failing, our payment service. Everything else looked perfectly healthy. That's when finance dropped the message. We're seeing real transaction failures. Now, this wasn't just noise. This was money, and it was actively breaking. Environment context. We were running on AWS, EKS cluster, multi-region setup with primary traffic in EU West 1 and failover in US East 1. The payment service was a Go microservice. It handled card tokenization and communicated with a third-party payment gateway. Traffic was around 1.5K requests per second during peak hours. We had RDS PostgreSQL for transactional data. Secrets were managed through AWS Secrets Manager, injected into pods via Kubernetes external secrets. CI/CD was GitHub Actions. Every merge to main triggered a build, pushed to ECR, and deployed via Argo CD. Monitoring stack was Prometheus, Grafana, and Alert Manager. Logs were centralized in Loki. Everything was standard, stable, boring in the best way, until that night. Initial symptoms: users were reporting failed payments at checkout. Front-end logs showed 500s from our API. Our service logs were more specific. Unauthorized request to payment provider. 401 errors. Consistent. Reproducible. But here's what didn't make sense. We hadn't deployed anything recently. Last deploy was 14 hours earlier. No config changes. No infra changes. Health checks were green. Pods weren't restarting. Network looked clean. Even more confusing. US region was fine. EU region was failing. Same code. Same container image. Different outcome. That's when things started to feel off. Investigation and escalation. First thought was provider outage. We checked their status page. All green. We tested from a local machine using the same API keys. Worked perfectly. So not them. Next hypothesis. Network or IAM issue in EU. We jumped into a running pod. Manually called the provider API. Same error. Same call from US pod. Success. Now we had a regional difference. We compared environment variables between regions. Everything looked identical at first glance. Same config maps, same secret references, same deployment manifests. But something was different. It had to be. We pulled the actual secrets mounted in the pods. And that's when we saw it. The API key in EU was not the same as US. Not even close. US had the expected production key. EU had something else. A completely different token. And it looked suspiciously short. Like a test key. Now the question changed. Not why is the provider rejecting us, but how did the wrong secret get there? We traced it back to Secrets Manager. EU secret value had been updated. Timestamp was 0158, 15 minutes before the incident started. No manual changes logged, no rotation job scheduled at that time. We checked CloudTrail. The update came from a CI role, GitHub Actions. That was unexpected. We don't rotate payment keys via CI. At least, we weren't supposed to. Now Slack was getting louder. Can we fail over EU traffic? Revenue impact is growing. We had to decide quickly. Failing over meant sending all EU traffic to US. Higher latency, potential compliance concerns. But continuing like this meant losing transactions. We initiated partial failover, shifted 60% of EU traffic to US. Error rate dropped, not zero, but manageable. That bought us time. Now we focused on the pipeline. Root cause. We pulled the GitHub Actions logs from the last run. There it was. A workflow triggered by a merge to main. A seemingly harmless change. Someone had updated a config file. But buried in that commit was a hard-coded fallback value. An environment variable for the payment API key. It was meant for local testing. The code had a conditional. If the secret fetch fails, use fallback. In production, that should never happen. But earlier that night, the secret sync job in EU had a transient failure. The external secrets controller failed to pull from Secrets Manager. For a brief window, the pod restarted without the secret. and the application fell back to the hard-coded key. Then the CI job ran. As part of a new step, it synced runtime configs back into Secrets Manager, including environment variables, which now included the fallback key. So the system overwrote the real production secret with the test key and propagated it across the region. Everything that followed was just the system doing exactly what it was told. Mitigation and recovery. First step was to stop the bleeding. We manually restored the correct API key in Secrets Manager for EU. Then we forced a refresh, restarted the payments pods. Within seconds, 401s dropped. Error rate normalized. We disabled the CI workflow responsible for syncing configs. Then we removed the fallback logic from the application. No secret, no startup, fail fast. We gradually shifted traffic back from US to EU, watched metrics closely, error rate stable, latency normal. Full recovery took about 47 minutes. Post-mortem reflection. What actually failed wasn't just a secret, it was the trust boundary between code and runtime. We assumed secrets would always be present. We assumed CI would never touch production secrets. We assumed fallback logic was harmless. Detection was also weak. We alerted on error rates, but not on secret changes, not on config drift, not on unexpected writes to Secrets Manager. Observability told us something was wrong, but not what changed, and the system quietly replaced a valid credential with an invalid one, without any guardrails. Engineering lessons. We removed all fallback secrets from production code. If a secret is missing, the service should not start. We locked down IAM permissions. CI pipelines no longer have write access to production secrets. Ever. We added alerts on secret mutations. Any change in Secrets Manager now triggers a review. We introduced checksum validation. Applications verify that secrets match expected patterns before using them. We separated config sync from runtime environments. No more bidirectional flow. CI writes artifacts. Runtime consumes them, never the other way around. And we added regional parity checks. If two regions have different critical secrets, we get alerted immediately. In the end, nothing was hacked, nothing was breached. The system behaved exactly as designed. And that was the problem.